Welcome, sir. We'll start within 15 minutes. Sir.
10 minutes, yeah. 10 to 15.
Sir, good evening from here, sir. Okay, sir, are we audible?
Try again, please.
Sir, good afternoon, sir, from here. Are we audible, sir?
I'm sorry, I can't hear you.
Okay. Just a minute, sir.
Okay. Now I have sound here. Okay, go ahead.
Now are we audible, sir?
Yes.
Yes. Okay, thank you for joining, sir. Within 10 minutes, we will start the session, sir. Yeah. Done. Everyone settle. Audio. Zoom.
Just add your phone if you want. See that.
Should we
Yes, sir.
try the screen sharing?
Yes, sir. You can. So the screen is visible, sir. Yes.
Do you see it?
Yes. Yes. Shall I start? Okay. Yes. YouTube. ARP. Okay.
Good evening, Professor. Can you hear us?
Good morning.
Yeah.
Yes, I hear you.
Yeah,
Can you hear me?
yeah, of course. So it is 2:30, nearly 2:30, 2:25 p.m. In India. And we are here, joined here, and many of us will join online also. Many people will join online. So it will start at 2:30. So we will allow others to join also. Meanwhile, I will like to introduce ourselves. No, we are from the Department of Physics. And as you know, the student chapters, SPIE and OPTICA, the student chapters, they are organizing this event. Morning, we had two lectures by one on fundamental aspect and another on industrial aspect, given by two professors from India. So here we have our faculty advisor, Dr. Sasti Kumar with us. And this program shall be moderated by Dr. Shankar Narayanan. So question answer, professor of physics. So the question answer session will be coordinated by Shankar Narayanan sir. First, we will have your lecture followed by question answer sessions. And probably there will be questions in the chat, and Dr. Shankar Narayan will read the questions to be asked to you. And those who are in this hall, it's composed of PhD scholars, masters, and undergraduate students, and faculty also. So any questions from these students will be directly asked to you at the end of the presentation. So this is the methodology which we are adopting in this session. So once again, I welcome you for and also thank you for joining online. So first at 2:30, this session will begin with the introduction by the SPIE OPTICA student chapter office bearers. Then Dr. Shankar Narayan will take over. Thank you.
Thank you very much. And welcome to everybody.
You should be visible there.
வாங்க இப்ப ஜாயின் பண்ணிருக்கேன். ஆடியோ ஒண்ணும் வரல. வைஃபை தானே அங்க போயிருச்சா? நான் என்னடா அவனு சவுண்டே காணாம கேட்டு இருக்கேன். ஓ அங்கே மாதிரி செனட் மாதிரி தானே? ஆமா சிரிச்சிருவாங்க. அப்படி ஸ்டாக் ஆயிருக்கு, அப்படியே நின்றுச்சா? அப்ப இது எப்படி மக்கள் சொன்னாங்களா? நான் அப்பதான் ஆன் பண்ணேன். இங்க தான் நான் வந்துட்டு மெயில் பார்த்தேன், இங்க வரேன்னு சொன்னேன். இது சரி 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 சரி. ஓகே ஓகே ஓகே. இந்த சிலையில தான் இருக்கு, அதே சிலையில தான் இருக்கா? ஓகே ஓகே.
அங்க தெரியுது. ஹலோ அவரு
Hello.
எஸ் சார், திஸ் இஸ் ஸ்ரீராம் here.
Oh, nice to see you.
Yes. Shall we start?
Okay, Professor, sorry for this technical glitch. Now we'll move on to the session with a brief introduction. So As we move forward to the most anticipated part of our program, it is my distinct honor to introduce a true luminary in the field of physics, Professor Pierre Agostini. Professor Agostini is a globally renowned French physicist whose pioneering work in attosecond science has transformed our understanding of ultra-fast phenomena. He is particularly celebrated for his groundbreaking contributions, including the observation of above-threshold ionization and the development of the reconstruction of attosecond beating by interference of two-photon transition, also known as the rabbit technique. This innovative method is essential for characterizing attosecond light pulses and has opened new avenues in the exploration of electrodynamics, pushing the boundaries of our knowledge of the quantum world. In recognition of his extraordinary contributions to science, Professor Agostini was jointly awarded the Nobel Prize in Physics in 2023 for his pioneering experiments with attosecond light pulses. His work, which enables the observation and measurement of the fastest events in nature, has profoundly advanced our understanding of atomic and molecular processes, laying the groundwork for future breakthroughs across various scientific disciplines. Beyond the Nobel Prize, Professor Agostini has been the recipient of numerous prestigious awards, including the Gay-Lussac Humboldt Prize, the Huplaus Fellowship from the Dutch Foundation of Fundamental Research on Matter, and the William F. Meggers Award in Spectroscopy from the Optical Society of America in 2007. Currently, Professor Agostini holds a distinguished position at the Ohio State University, where he continues to inspire the next generation of scientists with his groundbreaking research and unwavering dedication to the advancement of science knowledge. Thank you, sir. Now I invite Professor Shankaranarayan sir to moderate the session.
Thank you, Professor Pierre Agostini, for delivering a lecture on this occasion. Thank you so much for your time and effort. And I request all the audience to take up the questions at the end of the session. The session is also going in live stream, so those who are joining in the online, they can also post their questions in the chat box. Those questions can be answered after the lecture. If there is, sir, if there is any hiccups, you can please continue, because anyway we are following you. Yeah, please. Thank you so much, sir.
Should I start?
Yes, please start, sir.
Okay. Well, first of all, let me say that I am very glad to be in India, even if it's only virtually. All right, and welcome to everybody there, and good afternoon, since it's afternoon there. All right, so as it has been said, about a year ago, the 2023 Nobel Prize in Physics was awarded for experimental methods that generates attosecond pulses, I forgot, of light, of light, for the study of electron dynamic in matter. All right. So, in this talk, I will briefly review the two known techniques that generate attosecond pulses of light. The first one is based on high harmonic generation in gases, and it goes back 30 years at least. The second one is based on XFEL and is much more recent. Finally, last week, appeared in Science, another one, which produces sub-femtosecond electron instead of photon pulses. So I will review that. I was lucky enough to touch it in Science last week. I will then review a few applications and applications on photoionization delays, on recollision physics, and on charge migration. All right, so the first technique is attosecond pulse train, and is based on high harmonics, but high harmonics created by a long laser pulse. By long, I mean a few femtoseconds. So high harmonics were discovered in the mid-80s by Laureate and co-workers in Saclay in France. And the driving laser at that time was only picosecond, 40 picosecond. And it had to be focused very tight to reach the intensity of a few hundred of terawatt per square centimeter. Harmonics were reported up to order 21, which is by nowadays standard not very much, but at that time it was a big surprise and very exciting. And by the way, nobody thought about attosecond at all at that time. That's the that year version in Riken, and you can see here the result of 40 years of ultrafast. The laser is now 40 femtosecond, it's not picosecond, and it has much more energy per pulse, and it can allow to use very loose focusing. The focal length was 2 meters in that experiment. Orders up to 350 were produced by pulses, and those were equivalent to pulses of 100 attosecond or so, and just up to the water window. Sorry, can you hear me? I'm sorry.
Please go ahead, sir.
Do you have a question?
No, please go ahead.
Okay. So the number of AtoBeam lines in the world is huge. I discussed a little bit with Anne and Terence, and we don't have a list yet. So I'm not sure if there is one in India, maybe in Canada. So I don't know. If there is one, let me know. Okay. All right. From the inverse Fourier transform, we know that if we have a spectrum like this in the harmonic spectrum look as a large number of orders, it will, or it can transform into a train of possibly very short pulses if the spectral phase is constant or a linear function of frequency. The question was unanswered until rabbits, and the question was, is the phase really constant or linear function of the frequency? So when Farkas and Todd published their paper in 1992, suggesting the possibility of attosecond pulse train, it was more or less ignored. Actually, the phase, we had a theoretical investigation of phase in this calculation by Antoine Angelier and Maciek Levenstein back in 1996. And the phase was, looked completely random. It was not very encouraging for attosecond pulses. But there are two aspects, or there are two sides in high harmonic generation. One is the single atom response, which is illustrated here. And the next one is the collective emission, or the classical emission using the phase matching, of course. The calculation for the single atom response was almost random, and it did not, it was not very encouraging for attosecond. So it's only in 2001 that the rabbit measurement revealed the phase, which was almost linear in the far field emission, thanks to the phase matching. That is the reason why high harmonics emit attosecond pulse train. In the cutoff region here, the phase is constant, but unfortunately there are not so many photons there. But still, that was the technique that was used by Ferenc Krauss to generate isolated attosecond pulses. That is the historic rabbit setup back in 2001, and it was mostly due to the I can say to the genius of Harmhit Müller. I don't want to describe it here. I just want to say a word about the two glass windows that were used for tuning the atom pulses in time, and that was sent as a gift to the Nobel Museum. That's one thing. The other thing is about the pinhole. So the rabbit technique we invented back in 2001 is the technique we characterize attosecond pulse train in the spectral domain. So it's very analog to frog for femtosecond. In that historic version, the pinhole was responsible for creating the attosecond pulse train by isolating in the far field the emission with the linear phase, although it was there for a completely different reason. It was there for stopping the infrared beam. So sometimes you need a little bit of luck in experiments. Okay, Now, the other technique using high harmonic generation is when your driving laser is a few cycles instead of long pulse. So in that case, the spectrum, the harmonic spectrum, turns into a continuum, often called a supercontinuum, and the Fourier transform of this is a single attosecond pulse. So this was, discovered essentially the same time we published the rabbit paper in 2001. And it was invented in Parents Group in 2001. To measure those very short pulses, Ferencz group used a technique which is completely different from the rabbit technique. It's the pulse is measured by the so-called stretching technique, and that's directly in the time domain. So the Attosecond pulse ionize an atom, an infrared laser, and the electron momentum just follows the vector potential of the laser, and so it goes up and down, and from this variation one can derive the pulse length. The first pulse was about 530 attoseconds, as it was reported in 2001. A few years later, the Milano group, Sansone et al. in 2006, reported a pulse which was already much shorter, about 100 attoseconds, and it was almost a single cycle pulse. And it took another decade or so to reach the attosecond pulse current record, which is according to that paper of Kaunitz et al. In Werner group in ETH in Zurich, it's 43 attoseconds. And here you have an illustration of the Fourier transform, of the spectrum of the pulses of such short pulses, both in neon and argon. The driver laser was a mid-infrared laser with a 2-cycle pulse length, and this is the reason why they could get this huge continuum spectrum which transform in such short pulses. All right, okay, and now we jump a few decades ahead, and we go to the XFEL. So there are a few XFEL facilities in the world, and both the LCLS in California, in Stanford, the Germany European XFEL, the Swiss XFEL, another one in South Korea, and of course the Sakure XFEL in Japan, which is almost as old as the LCLS. I'm not sure if there is one in India right now, but if there is, just let me know. Okay, this is for a very recent paper. I mean, 2019, a paper by Juris et al. And all the, actually there are a large number of authors in this paper, since, as you know, it's kind of difficult to have a laser time on such a facility, and so people have interest to group each other. This result was really wonderful, because if you look at the pulse energy, it's orders of magnitude larger than everything which has been obtained with the high harmonics. So, and also the wavelength is much shorter than that anything which has been obtained before. And the energy of the pulses is several hundred of electron volts. So such a laser is now available for use for anyone who can produce a reasonable program to use it for 2 weeks. It's possible in principle to do nonlinear optics with such energy, such pulse energies. And so this is really a new laser, and as they say in their paper, these pulses paved the way for a new era of Attosecond science. All right, I will now just say a few words about something I discovered last week in Advance in Science, and it reminds me of the Harben Sewell and the 1919 Nobel Prize of Chemistry got, because that's exactly the kind of things he wanted to do at that time. And I remember when he visited Ohio in 2011, we had very long talk about that. So this is a technique which combines electron microscopy and Attosecond pulses. I'm not going into the details of that, but they have an Attosecond pulse that first generate electrons on a photocathode, and after second harmonic generation. So the electron pulse is only 100 femtosecond at that stage. But then using a special technique called optical gating pulse, they are able to reduce the pulse to sub-attosecond pulses, to sub-femtosecond pulse, sorry. And they quote 625 attosecond, although they don't have really a measurement of those pulses. So this is really the first time I see that. And the big thing now is that this electron pulse is 200 kilo electron volt of energy. So this is something you can hardly dream of using high harmonics. And So, yeah, we'll see a few applications of that in a moment. So, the first application we had is historically the first one that was predicted in the 1986 paper by Vignard, Tayeb, and Mackay. The paper says that the rabbit phase is actually the sum of the Attosecond pulse train phase, which is responsible for the Attosecond pulse train, and also of two other phases, which are small corrections, so one can say. In the first paper, it was just calculated, but now there are ways to measure them. So these corrections has two parts. First part is coming from just from the above threshold ionization 2-photon matrix element. And it's not very interesting because it can be calculated completely analytically. And the second is much more interesting for theorists, and that's the Wigner delay. So in that, since 2001, I think there are maybe tens of publications on the problem of femtosecond or photoionization delay. So this one is an experiment we did at OSU in 2014, and I'm just showing as an example. The Wigner delay is kind of difficult to measure because it has to be extracted from a total phase which is much bigger. So in that case, we took the difference between the phase of those gases and helium, and the phase of helium can be calculated. So the Wigner delay can be calculated for those three atoms. And yeah, the interest there is to compare two theories. So there are a couple of theories to which it's compared on those graphs. Okay. So some theorists were very happy with it. The second one is, I don't know if you recall, some of you probably recall, back in the 90s, the big surprise was by the non-sequential ionization, double ionization of helium. This was, a surprise of several orders of magnitude. So it was explained qualitatively by Paul Corkum in this famous paper. If the electron, he says, if the energy of the electron as it passes the ion exceeds the E to E scattering energy, the ion can be collisionally ionized by the electron that has left the atom only a fraction of period earlier. So we set to check this theory quantitatively, and this is the result. Okay, this was measured in argon, double ionization of argon, and this is a theory calculation in the group of Ohio State, and this is the experiment, and you can see that there is a very good agreement between the two. So this is not yet published. Okay, the other the application I want to tell about today is the charge migration. So if you ionize an atom from a molecule, for instance, in this NH2 group in phenylalanine, and that's a rather old experiment now by the Milano group of Mauro and Nisoli. So if you ionize the atom, an atom there, the whole density which you create will move around the molecule, and in principle you can try to measure it as a function of time. Okay, in this case, in that experiment, they use a laser pulse to doubly ionize the molecule after a delay. And then they observed this oscillation of the in the doubly charged ion. And this oscillation was too fast to be due to the nuclei motion. But it follows the whole density, as this has been shown by density functional theory calculation. So it's not the direct, but it's very complicated to check the result. But they have done it in that 2014 paper. Okay, and to end this applications, I show this experiment done by the 200 kilo electron volt electron pulses. So those are laser-induced electron dynamics in the reciprocal space of graphene, and they have taken snapshots of this electron density in the graphene, and you can really see the changes, and the changes are of the order of femtosecond or so. So that's the closest to a picture of an electron so far. I'm saying the closest of a picture of an electron because I'm sometimes asked, please send me a picture of an electron, and unfortunately I cannot do that yet. Okay, so if you take home messages, so attosecond pulses are now 22 years old, and that's 10 to 26 attosecond. The shortest pulse is 43 attosecond long, as we have seen. By comparison, the precision, the current precision in atomic clocks, according to Wikipedia, is 1 second, 400 million years, and that's 370 attosecond per second. So I'm not sure this 43 attosecond can improve this number, but maybe it can. The shortest delay which has been reported is took 247 femtosecond. That is 10 to the minus 21 seconds. But there is no light pulse that short yet. We are still in the attosecond range. Finally, there are two harmonics, two applications of the harmonic spectra, but not in the attosecond regime, which has been proposed by my two co-prizers in their lecture in Stockholm last December. One is an application of the soft X-ray spectrum of the harmonics to the profile metrology, the 3D profile metrology. So this has been published already. And yeah, especially that application inference class group of the Fourier transform electron spectroscopy to the detection and to the early detection of cancers is very, very exciting. All right. I think I will stop that. Thank you.
Thank you, Professor. Now the session is open for questions, both from offline and online. Yeah, please.
Hello, Professor. Actually, I have when I first heard about this Nobel Prize topic on attosecond pulses, I was thinking it is in electron capturing scale. So whether this would it was like I understood that the electron dynamics can be measured. Does this violate Heisenberg's uncertainty?
Well, okay. I'm not sure about it, about Heisenberg uncertainty there. Why do you say that?
It is like attosecond pulses. It is like a camera can capture in millisecond zones, and an electron movement can be captured with attosecond time scale. Like electrons motion, like time period of an electron in an orbit, not orbit, like a cloud. It is in the order of 10 power minus. This is an attosecond range. So this was the question which I had, like when I was into this attosecond.
Okay. Well, first of all, there was no measurement of electrons with optical pulses. Only this experiment with electron pulses of 200 kilo electron volt energy are recording, according to that paper, are recording the electron density as a function of time in graphene. So I'm not sure that that's against Heisenberg principle yet. Okay, if you can find the T's, well, actually, the result is not very clear yet. It's only a few, images that have been recorded, for the moment, I don't think there's any claim that it's, it's against Heisenberg. So let's take a look at the future.
Okay, Professor. And one more question. You mentioned about this higher order harmonics in this. My question is, it is only because of this ionization. Is it only because of this ionization the extra energy is provided, like for attosecond pulses? I came to a conclusion that after this electron tunneling, and when it that is after this ionization, when it comes to its original, when it recombines to its original state, it emits some pulses, like emits some frequencies. These were the reason for, this was my understanding. I thought this is the reason for the the extra harmonics produced. So is it purely out of this? Like what was accounting for that extra energy?
Okay, I'm not sure I understand the question. You talk about harmonics generated by excuse me. You're talking about attosecond pulses generated by harmonics.
Yeah.
And you're talking, what is the reason it's limited to, for the shortest one, 43 attoseconds?
Sorry, Professor.
Is that your question?
My question is about this I thought like it is purely out of tunneling. Once the atom gets out, like in that zone, out of its zone, because of tunneling, and when it combines with the incoming frequency, and it has to come to its original state. Like it can't escape entirely. So once it comes to its original state, it is emitting some extra frequency.
Well,
Maybe I will write to you,
okay.
Professor.
I'm still a bit confused. In the case where your driving laser is very short, 2 cycles or so, then the spectrum of the harmonics is a continuous spectrum. You get that? And in the Fourier transform, in the time domain, this corresponds to a single very short pulses, or as short as your spectrum allowed. Okay? That's the reason, well, that's the limit. Actually, in the paper of the Optics Express, the 43 attosecond pulse, they claimed that the spectrum was limited by the mirrors. And they say if they could change the reflectivity of the mirror, they could reach almost 1 atomic unit of time, that is 24 attoseconds. So in that case, it's just the spectrum which is the limit of the time.
Thank you, Professor.
Thank you, Professor. I think Professor Prem Bisht has a question.
Yeah, thank you very much for such an excellent overview of the current research in this field. So we all are informed about this. Um, I actually have come from IIT Madras to give a small information to these students here. With reference to this particular presentation, in one of the slides you showed a vertical setup in which some time-resolved X-ray was mentioned. Can you say something more about that? Thank you.
Okay, I'm not sure I quite understood the question because the audio is not very good. Could you repeat, or could someone repeat the question?
Yeah,
You-
am I better now? So in one of
Yes.
the slides, you had showed a vertical sort of a system in which you mentioned of time resolved X-ray or X-ray imaging.
I'm not sure which slide you mean. Do you mean the electron spectroscopy?
Electron spectroscopy, exactly, yes. Can you say
Okay. Okay, let me. Okay, I could share again the screen.
This one, this after this.
exactly the same slide? Exactly this slide number 17, yes.
Okay. You have the reference here. So, yeah, as far as I understand, they have a laser here, which is fixed double, and then this laser is sent to emit electrons. And this electron pulse is, yeah, normal, is 100 femtosecond or so. Okay? But then they use this Attosecond pulse here to for what they call the optical gating. Yeah,
Okay.
and they well, there is another figure in the paper which is a little bit, which is a deal of this, where this thing is where the Attosecond gating is happening, and then they end up with this the so-called gated electron pulse, which is less than 1 femtosecond, according to them. So, and in the application, they propose this electron.
Sir, your voice is breaking.
Acid. Yeah, yeah, is the was and one.
Sir,
I could say
sir, your voice is breaking. Sir, your voice is breaking. Your microphone.
Did you
Hello.
hear me?
Yeah, your voice is breaking. Can you please check your microphone? Okay. Sir, sir, can you hear me?
Yeah.
Okay. Take the next question. Sir, the next question. Hello, can you hear me?
No.
Oh, the next question is, what is the current calibration limit to tune the measurements of phase change of electron transport medium in rabbit model?
Okay. Uh, what is the
What is the current calibration limit to tune the measurement of phase change of electron transport?
limit you mean electron current should be?
It's not clear to us. The
What-
audio is not clear to us.
We did the experiment as far as the electron count was about 1 count there. Question?
Any other questions from the audience? Sir, can you hear me? Yeah. Sir, it's nice to see. Yeah, it's nice to see that we are able to see the electrons floating around in the last slide with your attosecond pulses as a wonderful application. I just want to know, in simple terms, how do we explain the Wigner delay?
Okay. If both central, yeah, you will the acceleration decelerate. Compare on with then that time to be different. Yeah, and this is big difference. Different of the next
So,
yeah, is different. Data.
yeah, thank you, sir. Yeah, if any other question from audience?
Hello, sir. This is Sriram here. Sir,
Right.
thank you for accepting our invitation. on behalf of
Right.
NIT SPIE and OPTICA. Thank you, sir. Sir, you're not audible, sir, actually. எப்படி? Thank you, sir.
Are you planning?
So, due to some technical issues, we are not being able to hear you, sir. Actually, we are not able to hear you clearly, sir. So, but we were able to fully listen to the whole presentation, and we have some queries, and we hope that we can clear that through mail or some other way later on. So, I'm giving the mic to Dr. Sangasa.
Sir, once again, wholeheartedly, we, from the Department of Physics, the SPIE OPTICA chapter, student chapter of NIT-Trichy, we wholeheartedly thank you for accepting our invitation and connecting to us through online. It was really a very pleasure listening to you. And even though we had a little glitches in the last moment of question and answer session, we are able to follow your lecture completely. And we thank you once again. And I'm sure this is going to be an inspirational lecture for many of the young students of the participants of the symposium. Thank you once again. Thanks a lot. Thank you, audience. Yeah.
Should I?
So if people wants to have a photo session, you can keep your video on. Just a photo session, sir. Just for a few minutes.
Yeah.
Others can also join through online with the video. We'll stand here. இதை மறக்காதீங்க. Okay.
Next வந்துட்டு ஆஃப்லைன்ல வரதுக்கு next we are expecting ஆஃப்லைன்ல
Okay, thank you so much, sir. Thank you so much. Hope we'll meet you down the line in the offline. Thank you. Yeah. Bye-bye.